Welcome to this video. We're going to learn some more about simple harmonic motion. The first thing to look at is angles. I've written down some angles in radians here. They're not very big, as you can see. If we want to see the degrees, it only goes from 0 to about 23 degrees. If we take the sine of each of these angles, look at this. It's 0, 0.05, 0.1, 0.15 almost, and all the way down to the end, the value of theta almost perfectly equals sine of theta. Now, the percent error gets bigger as we increase, but the point is that when we're dealing with small angles, the sine of theta almost exactly equals the angle theta itself. But this is only true when we're talking about the radians of theta, not the number of degrees that theta has. So let's take a pendulum. Here's the center position. We're imagining the pendulum is swinging back and forth, and it stops and is at rest right here. The forces are gravity and tension, and I've shown also the angular displacement of the pendulum. How many degrees to the right has it been moved? We're going to make components for gravity, but we're going to use tilted y and tilted x axes. So there's an x component on that axis, and there's a y component that's parallel to this y axis. Now, we know that these two lines are parallel. So this angle theta equals this angle theta. And these two lines are parallel. So this angle theta equals this angle theta. When we look at the right triangle, FGX is opposite theta. So it equals hypotenuse sine theta. Now I'm going to move FGY over to here, onto the axis. Because I've taken care of FG, I've written it with components, I don't need FG there anymore. Tension and FGY perfectly balance each other out. So the net force is just FGX. I've put a negative sign because it points to the left, and also it's opposite the displacement. When we plug in for FGX, mg sine theta, from here, what do we see? Look at this. Sine theta approximately equals theta at small angles. That's what we just learned in the last slide. So this satisfies the criterion, the condition, for simple harmonic motion. Specifically, this equation for the pendulum, here's the pendulum equation, it has the form of simple harmonic motion. Minus a constant times displacement is what the net force equals. So we've just proved that a pendulum is in simple harmonic motion, right? Well, not exactly. If we take our pendulum and we swing it back, here's what we've said so far. There's a net restoring force pulling it back to the center. As you get closer, the net restoring force gets smaller. A little closer, the restoring force is smaller. A little closer, even smaller. And at the middle, there is no net restoring force. So let's watch that again. On the other side, the farther we get, the bigger that arrow length is because the net restoring force grows. And that force always points back to the middle. But wait a second. Something else happens with pendulums. They are in circular motion, so they have to feel a force pointing toward the center. And the faster they're moving, the greater that centripetal force. So over on the edge, there is no motion, so there is no net centripetal force. But as we speed up, the force toward the center grows. And as we speed up, as we fall, the force grows more. And as we fall and speed up even more, the force is bigger. And at the middle, we're really fast, so there's a big centripetal force. And on the other side, we have the opposite pattern. So there's two different things happening. There's this restoring force, but there's also this centripetal force. So what's the deal with this? What's going on? Well, only this motion of the pendulum, only this component, satisfies simple harmonic motion. We call it the tangential motion. And the other part, the centripetal part or radial part, does not execute simple harmonic motion. We call this the tangential motion because it's tangent to the circular path. So only one component of the pendulum executes simple harmonic motion. What about a spring? That's much simpler. Here's our center point. We stretched it to the right. There's gravity, the normal force, and of course, because it's stretched, it's getting pulled back by the spring force. The normal force and gravity, they cancel out. So the net is just the spring force. As we get closer to the middle, that spring force is smaller, and then it's 0, and then it points the other way. And as we get farther, it's a bigger force. So this force restores the system back to equilibrium. And like we said, the net force is the spring force. But the spring force equals minus kx. So once again, we have satisfied the equation for simple harmonic motion. We have met the condition. So there it is, simple harmonic motion. A pendulum and a spring with a block, they both have a big net force at the edge because we're so far displaced. So at the edge, the net restoring force is at a maximum. What about acceleration? Well, net force equals mass times acceleration. These two are directly proportional. So whatever happens with net force is also going to be true for acceleration. Now I want to turn to speed. At the edges, what happens to the speed? Do we see? Let's slow this down. We change direction and stop very briefly. And at the middle, we swing down and we speed up. So we're speeding up, we're going fast, now we're slowing down, and at the edge we stop. So let's add that at the edges, the speed is 0. Okay, now let's consider what's happening at the center, at the equilibrium position. Here's the equilibrium position, here it is for the mass spring system. We know that because the displacement is 0, the net force is 0. And whatever is true for the net restoring force is also true for the acceleration toward equilibrium. But what about the speed? When the pendulum swings, it has potential energy at the edges, and that potential energy is being converted into kinetic energy at the bottom. So when the spring gets down to the bottom, it's got this kinetic energy, and so it's moving really fast. So at the center position, at equilibrium, we have changed all of our potential into kinetic, and so the speed is at a maximum. We're going to fill out our notes. We've said that whatever is true for net force is also true for acceleration. Why? Because F net equals ma. They are directly proportional, and so even the equation itself, the simple harmonic motion equation, we could even write it for acceleration. We're going to look at one full cycle. We'll start when there's no time that has passed, and at the end, we'll complete one full cycle, which means the time that has passed is 1 period. Halfway through, we've only completed half a period. Right here, we're 3/4 of the way through. And right here, we are 1/4 of the way through. Now, at the edge, displacement is at a maximum. And what else did we say? The acceleration toward the middle is also a max. Because if this is really big, then so is this. What about net force? If displacement is big, so is net force. This is at a max as well. And the speed is 0, because we're changing direction, and all we have is potential energy. We don't have kinetic energy here. But when we get to the middle, we've changed our potential energy into kinetic, and so now our speed is at a maximum. But the displacement is 0. We are at the center. And because the displacement is 0, because this is 0, so is the acceleration, and then so is the net force. So I'd like you to fill out the rest of this chart using what we've learned. And what are we seeing here in the picture? This is the progression of one cycle, or one oscillation. The period is the time it takes to complete one cycle. So I'll let you fill that out. The frequency, as we know, is the number of cycles completed per unit time. So in the case of SI units, that's per second. And the amplitude, what's that? The amplitude is the maximum displacement we reach from equilibrium. Now, to qualify as simple harmonic motion, you have to have the equation on the very top. Either of these gets you to simple harmonic motion. But we could say something more, which is, by simple, one of the things we mean is that the system must be frictionless.